Hello students, in this part we are going to deal with one of the most interesting experiments of the physics, that's Young's double slit experiment. In there we will see how the fringe patterns that we observe can be explained with the theory of interference. Hello students, so now we will discuss the most interesting experiment in the wave optics, that's the Young's double slit experiment. So let's see what's in there. Now in the Young's double slit experiment, I have drawn a schematic diagram here. You can see what's happening, why it is double slit. Young was the scientist who performed this experiment for the first time, Thomas Young, on whose name this has been named, and it's commonly called also YDSE. Young's double slit experiment. Now we'll see what this experiment is and what happens here. Now there is a source here. This source emits light, okay. Now this light falls on this cardboard where you have a slit. Now this slit is an opening from where the light can come out. So when you have a source here, it is emitting light everywhere, right? In this direction, this direction, this direction, everywhere. Now but the light that crosses this slit can only pass through it, right? All the other lights, they can't cross it. So what happens? The light will cross from here, and then what we have is we have another double slit that is placed here. Now this is the light that is coming from this point, okay. Now the light from this point will reach this and this point. Now if you remember the secondary wavelength theory, what happens is that every point that is present here will act as a source now. So that means from here the waves are coming, from here the waves are coming, it's like this. So a wave that is coming, now a wave that is coming from one point source, it will release the waves in coherence. They will be the coherent sources. If you remember, we discussed, because only when you have a coherent sources is that the interference will happen. Now why, that we'll see later on. Why is that only in that case it will happen. Now so they have to be coherent. Now since they are coming from the same source, single source, it is coherent. Now it is falling on the two slits. Now then they will interfere, they will meet somewhere. Now this is the screen on which we will observe the pattern. So you will see that you have alternate. This is the bright fringe, and then there is dark, bright, dark. What is this bright, dark? This is the redistribution of energy. Where you have more energy, it's positive, it's bright, positive energy, bright, and then the energy is not there, zero energy, so it's dark. Now from this I have drawn the schematic diagram. So this is source S, this is slit 1, slit 2. Now suppose I consider this at any point P, okay. So the light from this will reach here like this, light from here will reach here like this, okay. Now this is the source. Now from this source you can see that these two, it is placed here such that these two lengths are equal. This length is equal to this length, right? Exactly in the middle. So these two lengths are equal. Now a wave that is coming from here, it's originating here. So okay, so the wave will come out like this. Wave is going from here like this. It will originate from the same point. So you can see that initially they are in phase, right? Both of them started from here at time t equal to 0. They all started from the origin going in the same direction. They are coming from the same point. So they are in phase. When they reach here, again they will be in phase only, right? So whatever length it has moved will be the same length that this moves. So again here and here they are in the same phase. Now the waves are moving here like this. This wave is also moving like this. Now they are moving again. Now if you see here, it's very clearly visible that this length S1P is less than S2P. You can see it from here, it's visible from this. That means when it reaches this point P, both waves will no longer be in phase, because what will happen is that this wave, it may have reached somewhere, it's moving like this here when it reaches here, and it's possible that this wave which has gone longer path, it is something like this. Maybe it's in this state when it reaches here, because now they have traveled different length, right? So it's not that when it will be here, it will also be here. That may be a coincidence. That may happen. That is particular case. How it will happen? When that difference is exactly one wavelength. Because if this is the length, this is longer length. It has gone longer path. Suppose that longer path is only by 1 lambda. So if it is by one wavelength, they will again be in phase. But from all other positions, it will not be in phase. So it depends on this position. So suppose at this point the path difference is exactly 1 lambda. That means again they are in phase. Suppose at this point the path difference is lambda by 2. Lambda by 2 means this length or pi in terms of phase. So that means they are out of phase. So suppose here again the path difference is 2 lambda or 3 lambda, something like that. So 2 lambda 3 lambda means 0 path difference. In terms of phase difference it will be 2 pi 4 pi 6 pi. That's what is happening, and that's how we get the fringes. So we'll do the calculation for this quantitative part and let's see what happens. Now this distance is a small d. Now let's give the names to it. This is a small d. This distance is capital D. This is given to you. This d is called the slit width. Okay. So now let's do the mathematical part. What we'll do is that we'll try to find out the path difference. Okay. Now the waves from S1 and S2, they reach the point P with some phase difference and hence the path difference. Now since they have traveled different length, means it's like the two persons who started the race, initially they started from the same position, but one has moved a longer distance, one has gone only this distance. Two athletes start from here, one has gone only this distance, one has gone a longer distance. That means there is a path difference between these two. There is a difference in their state, right? So there is a difference in their phase. Similarly, that's what is happening here. When they go different length, there will be different path length, different phase. And what will be that phase? It will be S2P minus S1P, where you see here S2P is this length, S1P is this length. If you subtract these two, because in this portion, if you see in this portion, they have traveled the same length, so there is no phase change. But from here and here, the phase change starts happening. So we only need to consider this. Okay. So if you find out what would be S2P square minus S1P square. If you see here, S2P square is this. This is S2P, this length. We have, let's take a different color. S2P. So if this is this, what will be this distance? Now it is given that this happens at a height of y from this level, the origin level. Okay, y from this level. So from this level, S2 level, this length is y plus d by 2, right? Now this length S1 P, this length will be y minus d by 2. Right, it's visible from here because this length is d by 2, this length is d by 2. This height from the origin was y, so this is y plus d by 2, this is y minus d by 2. Now this is a Pythagoras, sorry, this is right angle triangle, so we apply the Pythagoras theorem. So S2P square will be equal to capital D square plus y plus d by 2 whole square. This is S2P whole square, we have applied in this right angle triangle. When you apply in the right angle triangle S1P, what you will have? D square plus y minus d by 2 whole square. So if you see the values here, this is d square plus y plus d by 2 whole square, path difference minus this. Okay. Now this we can write as S2P minus S1P into S2P plus S1P, and then solving this. Now if you solve this, what is the value that we are getting? This is d square by 4 plus yd minus d square plus y square plus d square by 4 minus yd. So what you get here, if you see, this will cancel with this, this will cancel with this, this will cancel with this. So what we get is 2yd, right? So we get 2yd. This can be written in this manner, S2P minus S1P into S2P plus S1P. Now what is S2P minus S1P? This is the path difference, right? If you see here, S2P minus S1P is the path difference. So S2P minus S1P, I have written delta. This is 2yd, I have found out the difference. And S2P plus S1P, what is this distance? Now if you see S2P plus S1P, Now practically what is happening is that this length y is very small compared to capital D. This is what happens, means this slit is this distance is very large, it is kept at a very far distance, and the fringes that you get, this length is very small. Actually this is minuscule. What I have shown here is that negligible distance I have exaggerated here just for clarity in picture, but it's very small. So in that case what will happen, this you can write as d plus d into 2d. So this is 2d. So what you get is this delta is yd by d. What is delta? Delta is the path difference. If you see here, y into d small d by capital D, where small d is the slit width, capital D is the distance between the slit and the screen. Now from here let's find out when the bright fringes will happen. When will the bright fringe happen? Bright means maximum. Maximum is constructive interference. For constructive interference, what should be the path difference? It should be multiple of lambda, right? Because if there is a path difference of lambda, that means there is zero phase difference, right? There is zero path difference because it's again the same. And when you have the same figures, then constructive interference will happen. It will add positively to it and you will have a constructive interference. But when there is a path difference of lambda by 2, means things like this. One is this, path difference of lambda by 2 means from here to here, kind of this. Like suppose this portion is interfering with this portion, like this, what will happen? This negative will add with this positive and the resultant will be null. Okay, so this is destructive. But when again it has moved this portion from here to here, if you consider this portion, so again it comes in phase. So that's how it's happening. So if you have a path difference of n lambda delta, you'll have a bright fringe. So where n is an integer, so n is, you can write y. What is y? If you see here, y is the height above the origin. From the origin, what is the position? That p, the position of the p we are talking. Okay. For n equal to 0, y naught is 0. What this means is that exactly at the origin you have the first maxima. So suppose this is the slit from here to here. This is the screen. So exactly here, this is y, right? So exactly here you have a maxima. Then if you put n equal to 1, y1 is lambda d by d. Then at a distance of, this is lambda capital D by small d. This is the first maxima, means here you have a brightness, total bright. This is again a total brightness. Again there will be total brightness at what? 2 lambda d by d. Means this distance is 2 lambda capital D by small d. Again it will happen when this y will become, this is y is measuring from here, 3 lambda d by d. Now if you see, a very interesting thing here is that the difference between these two, any of the two bright fringes, if you see, what is this? This is 3 lambda d by d, this distance, and up to this is 2 lambda d by d. What is this length? It's lambda d by d. Similarly, this is also lambda d by d. This is also lambda d by d. Now this is called the fringe width. This is called the fringe width. The distance between two maximas, or it could also be minimas. We'll see that it will turn out to be the same, and its value is lambda d by d, where capital D is in the numerator. You have to keep this in mind, keep the formula in mind. Now, so expression for the dark fringe width. Now we have seen here, this was for a bright fringe. You can find the positions of dark fringe, and from here you can find out this. When it will be a dark fringe, it's very easy to see here. When this will be equal to 2n plus 1 lambda by 2, means this is integral multiple of half of the wavelength. Means either you have lambda by 2 path difference, or 3 lambda by 2, or 5 lambda by 2, then you will have a minima. So what will be the values of y then? Y in that case will be 2n plus 1 lambda capital D by d. So if you put down the values, again you will have, what will be, n equal to 0 will give you lambda d by d, n equal to 1 will give you 3 lambda d by d, n equal to 2 will give you 5 lambda d by d. What is the part difference? Find out between any two consecutive dark ones. You will see that again this is lambda d by d. This is by 2, so this is by 2, sorry, this is by 2 by 2. So when you find out the difference, you will have again lambda capital D by d. So this is the fringe width that is called, and this is the distance between either two maximas or two minimas, and it's a constant. You have seen here that for any value that you get, between two maximas you always have the same differences. Okay, positions of the dark fringes we have seen, lambda 2n plus 1 lambda by 2. We put the values and then we get it. So expression for the fringe width is lambda capital D by small d. Okay, so what we see is that the expressions for the fringe width, so that the fringes are equally spaced on the screen. Okay, now let us see a question based on this. Now there are two slits. This is given 0.3 mm. Now the wavelength of light is 500 nanometer, so we convert this into meter. This is 3 into 10 to the power minus 4 meter. The number of maxima observed in the angular range this is. Okay, we have to find out how many maximas will happen in this. Okay, we have found out here is that beta is lambda capital D by small d, right? This is the fringe width, right? This is between, so suppose if there is a central maxima will happen here. First maxima happens here. What is this distance? It is this beta. Again there will be after beta, so like this. Now what is this beta? This is lambda 500 into 10 to the power minus 9 into capital D by small d. Capital D is not given. 3 into 10 to the power minus 4. What is the value that you are getting? This is 10 to the power minus 5 by 3 into 10 to the power minus 5. This is the value beta. Okay. Now what is this angle theta? Now if you write tan theta will be what? What is the tan theta for one fringe width? What is the angle for this one fringe? This is beta by capital D, right? This is the length beta, this is capital D. So this is the angular in terms of angle. So this is the angular fringe width. So what will give you is this tan theta is equal to, this is into D, right? Beta by D is 500 by 3 into 10 to the power minus 5. Now for small angles we know that this is equal to theta, which is 500 by 3 into 10 to the power minus 5, right? So what is the number of fringes in between this from 0 to 30 degree? From 0 to 30 degree means how many radians? 0 to 30 degree means you have from 0 to 30 degree. How many radians? It will be pi by 6 radians, right? If you convert this 30 degree to this. Similarly, you will have pi by 6 below, right? So what is the total radians? So this is the angular fringe width. Total radians are pi by 3. One fringe width has a angular width of this. How many fringes will be there in pi by 3? So the number of fringe will be the total angular width by the angular width of each fringe. So this will be pi by 3 by 500 into 3. So this 10 to the power minus 5, when it comes up here it is this. So 3 cancels out. So what you have here is number of fringes are this. Okay, pi by 6. So if you put the values, you had here 500 by 3. This total is 60 degree. So 60 degrees 2 pi by 6. So this is pi by 3 total. So we have pi by 3. Number of fringes is pi by 3 by 500 by 3 into 10 to the power minus 5. So this is this. So if you solve this, what are the values you are getting? This will make this 1000. So you have 3.14. So 31400 by 5. So if you see, this is 5630. So this is more than 600, right? You can see it. So if you see the options, the correct option is this. If you do this, it is 56, then you will have 0. So it's more than this. So if you take this pi, the value of pi as 3, you can find out the value will be around 601. So you can see it from here that we found out the number of fringe width by this method.
Having gone through our video lectures and video solutions may have cleared most of your doubts. For any further doubts, you may visit our site www.askitns.com. On the site, you will find a tab called Ask a Question. Click on that tab. Clicking on the tab will take you to the next page where you will find an icon Ask Experts. If you want to ask any questions, you can select the category of the questions. Like if you want to ask question from suppose wave motion, click on that option wave motion, paste your doubts here. If you want to attach some image of the question, you can attach the image also. Your question will be answered within 24 hours to 48 hours.
So students, we have seen the Young's double slit experiments and what are the fringe patterns in the fringe widths that occur in the experiment. So next we are going to deal with the intensity pattern of the same Young's double slit experiment. So stay tuned to Ask ITINS for more on this.